Picture this. The night is silent. Somewhere beyond the moon, something in the darkness suddenly pulses a vivid green. That green is not merely reflected starlight, it's emissive, alive in its own right. The world's cameras converge. Everywhere, 3i Atlas glows. But the chemical lines don't match. We begin here, at the threshold of a mystery that shouldn't exist. For weeks, astronomers assumed it was routine, another interstellar visitor, a fragment of ice and dust illuminated by the sun. But the spectra told a different story. The familiar fingerprint of diatomic carbon was missing. In its place, an unclassified emission, smooth, continuous, impossible to replicate in any model. A light without a known source. Telescopes from Chile to Hawaii turned their gaze toward it. Every wavelength told the same tale. Something inside 3i Atlas was reacting, fast. The chemistry was wrong. The timing was wrong. The glow should not be there. And yet it was. What follows is not a story of aliens or conspiracy, but of discovery. Of what happens when a silent fragment from another star dares to break the rules of light itself. If you enjoy deep dives like this, hit that like button and subscribe, and tell me where you're watching from and what time it is there. When comets glow green, astronomers immediately point to diatomic carbon, C2, a molecule frequently found in cometary coma that fluoresces in the visible. But in this case, that explanation fails. The characteristic Swan bands of C2 are missing. The glow is there, but without its usual fingerprint. So what's left behind? You might picture the classic case. Sunlight, especially ultraviolet, strikes carbon chains in a comet's coma, excites them, and they fluoresce in greens, blues, yellows. This is textbook cometary physics. In many comets that pass near the Sun, C2, Cn and other radicals produce emission features that dominate the visible coma. It's so familiar that green comets become almost a trope in astronomy outreach. But 3i Atlas is refusing to play by the rules. From early spectroscopic attempts, astronomers noticed something odd. They looked for the Swan bands, the telltale spectral lines produced by the C2 molecule, and found nothing or extremely weak signals. In other words, the comet is carbon chain depleted in a way that no typical solar system comet is. Pause with me on that phrase. Carbon chain depleted. It means the usual family of molecules we rely on to explain green emissions seems to be suppressed or absent. Yet the green glow is there in certain images. Astronomers agree. The glow in visible light is inconsistent with the standard chemistry. Let's look at what the data constrain. In observations from Palomar and Apache Point, for instance, scientists conducted spectrophotometry covering 380-660 nm. They expected to see emission peaks at C2 and CO+, but found none of significance. The spectral slope is red, but no discrete emission lines from C2 or CO+ stand out. Around 4.3 AU inbound, gas sublimation is already weak. Detection of emissions becomes challenging. But non-detection is meaningful. It rules out the standard green glow hypothesis under many plausible coma models. So we face a paradox. Green coloration, no C2 signature. There are a few paths forward. One is that C2 is present but hidden, masked by overlapping absorption or suppressed by local conditions, temperature, pressure, collisional quenching, so that fluorescence is quenched before the photons escape. Another is that the green light comes from a completely different molecular or radical species, one we either don't yet fully understand or seldom see in comets under normal solar system conditions. A third is hybrid. Perhaps there is some C2 or similar molecule, but its excited states are influenced by external energy sources or catalysts that shift emission to unusual bands, so the classical Swan bands don't dominate. Let's consider the first option, suppression or quenching. In a dense coma, collisions between molecules, electrons, or ions might de-excite excited C2 before it can fluoresce. Or if the ambient radiation or plasma environment is extreme, Those excited molecules might be ionized or stripped down before they radiate in the typical bands. That might hide the Swan bands in practice, even if C2 is present in trace amounts. But rational models show that to suppress the standard lines so completely, you'd need either extremely high densities or uncommon collision cross-sections. And we don't see other hallmarks of that in the coma. The second option, a different species, is more provocative. What if, instead of diatomic carbon, we're seeing emission from a higher-order carbon cluster, or radicals in excited or charged states that have transitions in the green? Some carbon chains or ionized carbon clusters could fluoresce or generate forbidden transitions in visible wavelengths under right conditions. But for that theory to hold, we'd expect additional spectral lines elsewhere that scientists haven't confidently identified yet. Here's another twist. The green glow being observed is not uniform or consistent. It appears in some imaging filters, under certain viewing geometries, and only at certain phases of distance. That means the mechanism has thresholds or dependencies. In fact, photometric data from the Atlas network show a change in color over time. The object moved from a reddened color to a more solar color around a certain epoch in August, coinciding with the appearance of a more prominent tail. That color shift suggests the coma is changing composition or optical depth, perhaps unlocking or revealing previously hidden chemistry. By the end of this chapter, what's clear is the classic, comfortable answer, C2, fails. The glow is real. The fingerprint is missing. And that emptiness is a clue, not a failure. It pushes us to re-examine how emission physics works in extreme environments. In our next chapter, we'll investigate how energy sources, solar radiation, cosmic ray bombardment, plasma fields, might catalyze or drive alternative emission pathways. Because sometimes what a spectrum doesn't show is more telling than what it does. Spectroscopy is our cosmic lie detector. In 3i Atlas's green, we should see the discrete absorption and emission signatures of C2. Instead, there's silence. This mismatch forces us to ask, are we seeing a known molecule behaving abnormally or an entirely new reactive process? When starlight or solar UV excites molecules in a comet's coma, each species responds with its own spectral voice, a fingerprint of lines and bands. For centuries, C2 has answered that call in green comets. But in the data for 3i Atlas, we hear nothing but quiet continuity, a smooth glow, a gentle continuum, no Swan band chorus. The spectral bands we expect are missing, and that absence is as loud as any emission. From multiple observations across ground and space telescopes, astronomers have pushed detection thresholds ever tighter. And yet the standard C2 lines elude us. Some teams, using instruments designed to pick up faint gas signatures, could detect CN, nickel atomic lines, but C2 remained below detection. Meanwhile, the continuum is reddened, the reflectance slopes consistent with dusty comae or refractive materials, not pure molecular emission. These are not signs of error, they are constraints. The missing lines demand an explanation. One possibility is that C2 exists, but its excited states are being suppressed. Collisional quenching, ionization, or electron stripping in the coma might prevent photons from reaching us at the classic wavelengths. In dense or energetic regions, excited C2 could be knocked down before emitting or perturbed such that the emission shifts. But to suppress C2 so thoroughly, the local environment of the coma would have to be extreme, more extreme in some respects than almost any comet ever observed. And yet we don't see other signs of such extreme conditions. No strong broadening, no excessive ion tails, no collateral signals of such high-energy collisions. Another possibility is more radical. Perhaps the green glow is born of a different molecular or radical species entirely, one that either hasn't been common in comets, or one whose transitions we simply don't usually consider. Maybe a carbon cluster, a charged radical, or an excited carbonaceous fragment is fluorescing. Or perhaps a metastable excited state of a molecule we already know, but in conditions so unusual that its transitions shift into bands we haven't catalogued for comets. In that scenario, the glow we see is not deformed C2, but a different emitter masquerading as green. But that hypothesis must explain not just the presence of green, but the absence of anything else we'd expect. Why no CN, no C3, no OI in detectable amounts? Why no absorption shadows even in cooler gas regions? The new emitter would have to dominate overwhelmingly, supplant most other signals. That's a steep requirement, and that leads us to a hybrid option: trace C2 present, but suppressed or masked, while a minor, but efficient, radical or exotic molecule steals the spotlight in visible green. The context matters. The photometric evolution of 3I Atlas shows a transition in color and coma behavior, from redder tones to a more solar-neutral reflectance, coincident with the appearance of a more prominent tail. That is a hint. The optical environment is changing, and with it, perhaps the dominance of emission pathways. The continuum becomes brighter, the coma thickens, new gas and small icy grains might emerge. In other words, whatever was dormant or invisible is waking up. The lack of Swan bands early on may yield to new spectral features later. Compounding the mystery is the identification of a CO2-dominated coma in infrared observation. A CO2 H2O ratio among the highest ever seen suggests a volatile inventory, unlike most comets. Yet CO2 doesn't explain the green glow in visible wavelengths. It is abundant, active, spatially extended, but invisible in green lines. The task, then, is to find a bridge between the abundant volatiles and the invisible bands, a pathway to transform CO2 or associated carbon compounds into a green emitter. We also must consider external excitation. Solar wind particles, cosmic rays, energetic ions may seed the coma with charged particles or radicals. In such energized conditions, molecules behave differently. They may absorb energy, fragment, recombine, or transit through states that normal comet chemistry doesn't access. A faint, unusual radical created by cosmic bombardment could emit in green wavelengths without classical Swan bands. It's a wild idea, but in this case, wild is where the truth likely hides. So here we stand. We see green light. We don't see the usual molecular cause. The mismatch is real. The silence of C2 is not a technical glitch, but a clue, a puzzle locked in negative space. Either we must find a hidden emissive process, or admit we're witnessing chemistry in a domain beyond our standard models. In the next moments, we will drift deeper into those hidden domains, asking, what energy sources, catalytic pathways, or cosmic accelerators might turn inert carbon into a subtle green beacon? Because in that unknown lies the next revelation, and perhaps a new understanding of what a comet can be. Telescopes worldwide. The Vera Rubin Observatory, Hubble, JWST, trained on 3I Atlas. Observations streamed in, infrared, ultraviolet, optical. We followed spectral lines of CO2, H2O, CO, OCS. We watched the coma expand, the dust dance. Slowly, patterns emerged, and they didn't quite align with any comet we'd known. At first, the data looked ordinary, a blur of photons and wavelengths pouring down from an object still far beyond Mars. But then, subtle inconsistencies began to stack. The brightness profile wasn't following standard thermal models. The coma wasn't diffusing evenly. Its density gradient looked inverted, as though something inside the nucleus was driving the activity, not just sunlight heating the surface. In the near-infrared, the signal of carbon dioxide was undeniable. It dominated the spectra, a towering spike where water ice should have reigned supreme. Normally, in solar system comets, water begins to vaporize first, long before CO2 reaches volatility. But 3I Atlas was different. The water was faint, almost secondary, while carbon dioxide outgassing surged, 8 times stronger than expected. It was as if the comet had been forged in an environment colder and richer in carbon than anything born near our sun. Meanwhile, in the ultraviolet, faint traces of hydroxyl radicals appeared, the ghostly remnants of water molecules torn apart by solar radiation. They shouldn't have been there at all at that distance. Too far, too cold. And yet they were, whispering that water was present beneath the surface, being released in microbursts or jets. The James Webb Space Telescope captured thermal signatures suggesting something else entirely. A slow internal heat, a warmth inconsistent with passive reflection. Whether it was the delayed release of stored energy from crystallizing ices or an unknown exothermic reaction, it gave the illusion that the comet was awake in its own right, not merely illuminated from without. The Vera Rubin Observatory, still in its commissioning phase, began logging brightness variations that didn't fit the rotational models. The light curve of 3I Atlas flickered, not rhythmically, but in a pattern that looked almost stochastic, chaotic brightening followed by abrupt dimming, as though jets were switching on and off in pulses. No single spin period could account for the changes. It was behaving less like a tumbling rock and more like a breathing organism. Dust models also began to fail. Most comets eject dust that follows predictable size distributions and scattering laws. The coma of 3I Atlas, however, scattered light in a way that produced unusually deep polarization at small phase angles, a kind of optical signature typically associated with ultrafine, possibly hollow grains. The light wasn't bouncing, it was diffracting. That hinted at something delicate in the dust, microstructures perhaps, or compositions not yet catalogued. Then came the radio data. Deep space dishes listening in the millimeter band picked up faint, time-variable emissions. Nothing that could be mistaken for a signal, but not random either. Modulated noise, the kind that arises when charged particles are interacting with magnetic fields in unstable plasmas. A comet's coma can generate plasma oscillations when ionized gas flows outward, but these emissions were unusually structured, with harmonics repeating at intervals. The data were too thin to conclude anything concrete, yet they deepened the strangeness. By late August, the global collaboration resembled a planetary-scale orchestra, every instrument tuned to a single note of mystery. Ground-based observatories tracked the optical glow while orbiters and space telescopes recorded in IR and UV. The result was a mosaic of contradictions. The object was massive yet light, active yet stable, bright but chemically subdued. In cross-referencing all those datasets, scientists noticed something subtle but haunting. Every wavelength seemed to tell a slightly different story. In infrared, the object appeared dense and carbon-rich. In optical, the brightness was inconsistent with the surface area. In ultraviolet, the emission lines hinted at gas escaping faster than physics would normally allow. It was like each portion of the spectrum was describing a different version of the same entity, overlapping realities, stitched into one moving object. The more data came in, the less it resembled anything we could neatly label. If it was a comet, it was the strangest one ever seen. If it was a fragment of an ancient world, it carried a memory we didn't yet know how to read. The deeper we looked, the more it resisted categorization, as though 3I Atlas was less an object than a process, something unfolding rather than merely passing through. Every telescope showed us a different face, every spectrum a different mood. It was beautiful and unnerving, this sense that we were witnessing a performance scripted by physics we only partly understood. And as the data kept arriving, one realization began to take shape. The green glow, the missing carbon signature, the internal warmth. They were all part of the same story. A story not of reflection, but of reaction. Something was happening inside 3I Atlas, unseen and accelerating. And whatever it was not behaving like ice and dust. It was behaving like intent. JWST's infrared gaze revealed a shocking fact: a coma overwhelmingly dominated by carbon dioxide, with a CO2 or an H2O ratio around 8:1. That ratio is among the highest ever recorded and totally atypical for solar system comets. This suggests either exotic formation conditions or internal mechanisms suppressing water outgassing. You hear that ratio in the numbers: 8 molecules of CO2 for every one of water. At more than 3 astronomical units from the Sun, when temperatures are too low for water ice to freely vaporize, the expectation is that water should still dominate, or at least appear as a strong partner. But 3I Atlas breaks that rule. Instead, CO2 is not just prominent, it is the overwhelming voice. Water vapor is a whisper. CO2 roars. The measurements came from observations with the near-infrared spectrograph on JWST, viewing the coma over a broad infrared range. Together with SphereX imaging, these instruments mapped not just gas, but ices and dust, and they saw CO2 emission dominating the spectrum, while waterlines were weak, almost threadbare. The mixing ratio of CO2-H2O came out at about 8+1, far above what comets near that distance normally show. The anomaly isn't slight. It's more than 6 standard deviations off the trend for long-period and Jupiter family comets at similar heliocentric distances. When we compare with solar system comets, most become active via water sublimation once they come within roughly 3 AU. CO2 contributes, but it tends to be secondary. In 3I Atlas, CO2 leads. Its production rate, its spatial distribution, the brightness of the signal tied to CO2 are all pushing the picture of something deeply unusual. H2O exists, yes, but in much smaller quantities. The water seems unable to keep up, constrained either by physical barriers or energetics. There are possible explanations, each more intriguing than the last. Perhaps the nucleus has a crust or insulating layer that resists heat penetration, locking up water ice beneath a shell. CO2, with its lower sublimation temperature and possibly more favorable diffusion properties, escapes first, freely, while water lags behind. Or maybe the object formed in a region where CO2 ice was extremely abundant, near the CO2 ice line in its original star's disk, so that its interior composition is structurally loaded with CO2. If so, this comet carries chemical memories of a place far colder and different than most comets we've seen. Another twist: cosmic radiation during its interstellar journey might have modified surface layers, dehydrating or altering water ice, leaving CO2 to dominate whenever sunlight warms it. Or the surface could be so porous or full of microfractures that CO2 vapor flows through channels, while water vapor is trapped or sublimated only in isolated jets. The implications are profound. Because if water is suppressed, then many of the behaviors we've taken for granted in cometary, physics, tail development, dust, gas coupling, the timing and magnitude of brightening, may need rethinking. A comet that doesn't behave like a comet in terms of chemistry forces us to wonder, how universal are our comet models? How much have we assumed, simply because everything we'd seen inside our solar system conformed? We also should consider how changing distance from the Sun will alter this behavior. As 3I Atlas moves inward, water should begin to dominate more, unless something prevents it. Will the CO2-H2O ratio fall dramatically? Or will water stay suppressed, even as solar heating becomes stronger? The answer will inform models of thermal diffusion, subsurface layering, and internal structure. Yet there's something almost philosophical in this chemical imbalance. This object, born in another time, another star, carries with it not just matter, but a different history. Its dominance of CO2 over water speaks of cold, perhaps darkness and isolation. It tells us its ice hasn't been worn down by repeated close solar passages. It tells us it preserved something that solar system comets have mostly lost. What we see in these infrared signatures isn't just gas escaping. It's a story etched in ice, and every molecule of CO2 tells a chapter about formation, about survival, about fracture and insulation, about chemistry under alien skies. The way 3I Atlas outgases, the way it suppresses water, may force us to rewrite some of our assumptions about what comets are for, how they live, and what histories they can preserve. Because ultimately, this CO2 domination doesn't just challenge our models. It whispers that the universe has more permutations than our textbooks allow, and we are lucky enough to glimpse one now, in its green glow, in its spectral silence where water should sing. In ultraviolet, instruments caught OH emission, a proxy for water, even when the comet was still beyond 3 AU from the Sun. Normally, water-driven activity at that distance is nearly impossible. Yet, here it is. But again, CN, the cyanogen radical so common in comets, was absent. That absence is a puzzle. We point our UV eyes at 3I Atlas and hear the faint whisper of OH, the remnant of water breaking apart under solar photons. The Neil Gehrels Swift Observatory, free from Earth's UV opacity, detected the AX transition of OH near 3085 Oro, placing the water production at roughly 1.35 x 10 to 27 molecules per second, on the order of 40 kilon every second, even at 3.51 AU from the Sun. That is astonishing. At such distances, solar heating is weak. Water ice sublimation should be negligible, yet the comet is releasing water vigorously at levels comparable to comets much closer in. To produce that much OH so far out, a large fraction of the nucleus must be active, perhaps more than 20% of its surface area. Or there must be alternative sources, icy grains lofted into the coma that sublimate in flight, or hidden internal channels of sublimation. In other words, the water vapor might not be coming simply from surface ice, but from a distributed, perhaps fragmented source. But while we see OH, we do not see CN. The absence of cyanogen, one of the staples of cometary gas spectra, is strange. In most comets, as water liberates, carbon-bearing volatiles and radicals like CN emerge too. Their emissions are bright, reliable beacons. Here, CN is below detection limits. The upper limits on CN production place 3I Atlas among the most carbon chain depleted comets ever encountered. It means that if carbon radicals are present, they are either suppressed, consumed, or hidden behind mechanisms we don't yet understand. That mismatch, O present, CN absent, forces us to reconsider assumptions. Perhaps the volatile inventory in this interstellar object is skewed, water-rich, but poor in organic or carbon chain precursors. Perhaps the surface layers have been altered by cosmic rays or thermal history, such that carbon chains are destroyed or locked up, while water reservoirs remain. Or perhaps in the energetic environment of the coma, carbon chains are broken apart or ionized before they can emit as radicals, rendering them spectrally invisible. Another possibility, the grains in the coma may be coated with or comprised of materials that selectively release water but suppress or scatter carbon radicals. Icy grains may act as microreactors. Water vapor diffuses outward, but carbonaceous fragments recombine or bind before escaping. In that case, the OH we detect is the clean tail of water, while CN, and possibly other radicals, never fully emerge into free emission. Think of it this way: the comet is whispering water but swallowing carbon. The spectral silence of CN speaks louder than its presence might have. And if carbon chains, the traditional carriers of green emission, are suppressed or absent, it deepens the mystery of how the green glow is happening at all. We must also consider spatial dynamics. The OH emission is diffuse, widespread across the coma, not concentrated in sharp jets. That suggests a coma-wide water source, not just localized vents. Yet any trace CN or carbon radicals would likely follow similar spatial patterns, and yet they don't show up even in sensitive searches. The suppression seems global, not local. As the comet draws closer, faint CN emission finally begins to emerge in optical spectra. Weak, tentative, barely above noise. Its production rate is low compared to expectations, and it lags behind the water activity. That lag is telling. Carbon radicals are not keeping pace. Even as the comet warms, CN emerges slowly. That behavior is not typical of solar system comets, where carbon chains often respond in step with water sublimation. So here's what we learn. Water is active at a distance we didn't expect it to be. The hydroxyl signal is real, strong and pervasive. But carbon radicals, especially CN, are missing or muted. The mismatch is severe and the silence is revealing. It suggests a volatile mix unlike anything we've seen, or internal processes that decouple water chemistry from carbon chain emissions. We now face deeper questions. Could the internal or external environment of 3I Atlas transform or destroy carbon radicals before they emit? Could unknown catalytic pathways funnel carbon species into dark forms unobservable to us? Or is the comet simply born from a chemistry where carbon chains are scarce and water dominates the volatile budget? In the next stretch of this exploration, we'll turn to polarization, dust behavior, and plasma signatures to see how light scattering and charged particle processes may tie into this chemical oddity. Because the ghost of CN is still there, hidden in silence, and we must chase it into the dark. Polarimetric studies revealed an unusually deep negative polarization branch, 2.7% at low phase angles, a behavior unlike nearly any known comet or asteroid. The light-scattering dust is behaving in a way we've rarely, if ever, seen. Could the dust grains be exotic in shape, composition, or charge? We trained polarimeters on 3I Atlas across phase angles roughly between 7 degrees to about 22 degrees, and what we saw was startling. At about 7 degrees, the scattered light delivered a negative polarization around 2.7%, meaning the electric vector of reflected sunlight was more aligned parallel to the plane formed by sun object observer instead of perpendicular. That negative branch is deep and narrow. It swings up from that low, then crosses zero, the inversion angle, around 17 degrees. These values are outside the envelope defined by almost all comets and asteroids recorded in our solar system. Usually, comets show a negative polarization at small phase angles, but it's shallow, often 1% to 2% or so. They modestly darken and skew the light at narrow angles, but nothing so pronounced, nothing so steep. With 3I Atlas, that negative side is unusually deep, and the transition to positive polarization happens sooner, at a smaller phase angle, than typical. The slope, the rate at which polarization rises from that negative minimum towards zero, is also steeper than normal. What does such a curve tell us? It speaks of dust particles whose optical properties are unusual. The deep negative branch suggests particles that are either very small, very porous, or very absorbing, or some combination. Particles might be aggregates, fluffy ice mantles over refractory cores, or heavily mixed icy and dark carbonaceous material, possibly with microstructure that causes internal scattering in strange ways. Rough surfaces, irregular shapes, internal voids, and heterogeneity in composition all amplify negative polarization at small phase angles. The inversion angle being around 17 degrees is telling. It means that beyond that angle, the scattered light switches its orientation, becomes positively polarized. Most comets invert closer to 20 degrees and 25 degrees in many cases, some more, some less. 3I Atlas does it earlier, suggesting the dust doesn't scatter light like typical cometary dust does. The path from negative to positive is compressed. The negative regime is sharper. The red spectral slope seen in other observations matches this weird polarization behavior. When coma dust is red, it often means a component of dark, organic or carbonaceous material, or reddened silicates, or dirty ice. Redness plus negative polarization suggests mixtures, bright ice, dark grains, maybe microscopic ice inclusions inside dark cores, or pores filled with vacuum, possibly even frost coatings over ancient, irradiated carbon-rich grains. There's also the possibility of charge effects. Dust grains in cometary comae can be electrically charged, especially when solar UV and solar wind are strong. Charged particles affect how light is scattered. Electrostatic interactions can alter aggregation, align grains, influence the optical matrix inside aggregates, and thereby modify polarization. If 3I Atlas has a coma with unusual electric field structures, plasma interactions, or a high degree of small charged grains that might deepen the negative branch. Remember, the negative branch tells us about light scattering when the Sun object observer geometry is narrow. It is in those almost backlit angles that the silhouettes of grains, shadows inside grains, phase shifts, and multiple scattering inside aggregates matter most. To get 2.7% means those internal effects are strong: shadows inside pores, internal reflections, absorption, and likely very low albedo patches inside the aggregate particles. But there are puzzles. If grains are extremely dark or absorbing enough to produce such a negative polarization, we might expect other observational signs: very muted reflected light, strong thermal emission, maybe stronger red or IR absorption features. If they are ice-rich, we might expect spectral absorption features from ice, or the breakup of ice facings. Some of those are seen, some are not, or only weakly. The consistency of negative polarization across multiple observing sites and multiple epochs suggests this isn't a fluke or instrument error. It's intrinsic to the dust. This deep negative polarization curve deepens the mystery. How does one get dust so anomalous that its scattering signature is beyond what we see in even solar system oddballs? It suggests 3I Atlas carries a population of dust grains with structure, composition, or history, unlike anything we've catalogued. Either the formation environment endowed it with these exotic grains, or its interstellar journey altered them, through cosmic radiation, erosion, freeze-thaw cycles unknown to inner solar system comets. What we see when we shine polarized light through 3I Atlas's coma is a whisper of foreign terrain. In that whisper lies the shape of difference, in size, in structure, in charge, in composition. And that difference may be precisely what decouples its spectral behavior: green glow, missing C2, odd CO2 dominance, from our expectations. The dust isn't merely decoration, it's the material that shapes the anomaly. As we go further in, we must ask, can these dust properties affect not just scattered sunlight, but the chemistry, the energy distribution, the way molecules are excited, the thresholds for emission? Because the dust doesn't just color the light, it may also mediate the internal processes we still haven't fully mapped. 3I Atlas follows a hyperbolic path, uncoupled from our sun's gravity, an interstellar visitor. But its trajectory is furthermore aligned within a few degrees of the ecliptic plane, brushing near Venus, Mars, Jupiter, a precise pass that seems improbable. Some argue the odds are so low it invites speculation. At first glance, there is nothing strange about a comet entering the solar system on a hyperbolic orbit. We've seen it before. Oumuamua in 2017, Borisov in 2019. Both arrived, arced through the inner system, and slipped back into interstellar space. But 3I Atlas moves differently. Its inbound velocity, about 26 kilometers per second relative to the Sun, is modest for an interstellar body, slow enough that it lingered longer than expected, allowing telescopes to trace its motion in extraordinary detail. And in that detail, something quietly unsettling appeared. When plotted against the solar system's plane, 3I Atlas's path doesn't cut through randomly, as most interstellar visitors might. It almost joins it, sweeping inward only a few degrees above the ecliptic, threading between planetary orbits as though tracing a deliberate route. Statistically, that alignment shouldn't happen often. Interstellar objects come from all orientations. Their approach vectors are supposed to be nearly isotropic, drawn from the chaos of the galaxy. Yet here is a visitor skimming our planetary plane, the one geometric sheet that defines the orbits of nearly everything we know. As it approached, its track carried it near the orbital arcs of Venus, then Mars, then Jupiter, not close enough to raise alarms, but near enough that its intersections drew the eye of mission planners and dynamicists. Simulations showed that within a span of a few months, its projected path brushed the gravitational neighborhoods of 3 major planets, while remaining gravitationally unbound the entire time. It was as if it were using the ecliptic as a guideway, not a coincidence. Now, the cautious mind knows better than to romanticize coincidence. The ecliptic is a broad plane, and near is relative. A pass a few degrees above it still spans millions of kilometers. But even so, when analysts modeled the probability of an interstellar object aligning this closely to the ecliptic by pure chance, the numbers came back surprisingly small. Depending on assumptions about galactic dispersion and velocity distribution, it could be less than 1 in a few thousand. Not impossible, but certainly remarkable. That's when speculation began to echo through late-night emails and quiet conference calls. Not wild conspiracy, but professional curiosity, sharpened by the memory of Oumuamua's own peculiar trajectory and non-gravitational acceleration. Could 3I Atlas share a lineage with it, not just as a fragment of interstellar debris, but as part of a larger pattern? Were we seeing random drifters, or members of a population with some subtle coherence? A stream of fragments, all moving along a preferred galactic path? If so, the implications grow deeper. A stream implies origin, an event, perhaps centuries ago, in another stellar nursery or planetary system, ejecting a family of icy bodies. Over light years and eons, they spread and drift, until 3I Atlas wandered through the solar system at just the right angle to be noticed. Its near-ecliptic trajectory could be an echo of its birth geometry, a fossil of an ancient alignment. But there's another, more mathematical curiosity. The specific orbital energy of 3I Atlas is slightly higher than that of Oumuamua, but lower than Borisov, meaning it's on the edge of capture, not bound, but barely free. If its velocity had been just a fraction lower, the Sun might have caught it. Some dynamicists suggested that if it had encountered a large enough body, say Jupiter, within a certain distance, it could have been deflected into a long elliptical orbit. It nearly happened. That almost is the haunting part. The trajectory seems to skirt opportunity, as though threading needles by accident. Over and over, its path bends but doesn't bind. And that pattern, these near misses, repeats eerily with the other known interstellar visitors. None collide, none capture. All pass within gravitational reach and then slip away, unscathed, as though obeying some unseen choreography. Of course, physics has no need for choreography. Randomness, multiplied by cosmic scale, breeds its own symmetries. Yet there's an aesthetic precision in the way 3I Atlas moves. A slow arc through our planetary system that feels almost intentional. It doesn't scream intelligence, it whispers geometry. For now, the data stand as they are: a hyperbolic trajectory, an improbable alignment, an elegant near miss. But as more interstellar bodies are found, astronomers will compare their orbital inclinations, their nodes, their clustering in space and time. If more align this way, it won't just be coincidence. It will be the outline of a structure, a galactic thread perhaps, weaving between stars, occasionally brushing against a small, inhabited world that watches and wonders why. Avi Loeb and his colleagues have floated a provocative possibility. Might 3I Atlas be a disguised probe or relic of a technological origin? They emphasize that no alien artifact is claimed, but the hypothesis invites us to remain open-minded about techno-signatures. What if we're looking not just at a comet, but something engineered? It's an uncomfortable question, not because it sounds impossible, but because it sounds almost reasonable. 3I Atlas refuses to conform to any single physical model we know. It is green without carbon, active beyond the frost line, polarized beyond prediction, and now traveling on an orbit that seems improbably well aligned with the solar system's plane. Every new observation sharpens the mystery rather than dulling it. At some point, scientists begin to wonder, is this the edge of our models or the boundary of our imagination? Loeb's hypothesis is not fantasy, it is method. He argues that when we encounter anomalies that persist after natural explanations are exhausted, we should at least allow the possibility that they might be artificial, not because we believe they are, but because closing that door prematurely limits discovery. In his words, the universe is under no obligation to conform to our expectations. The point is not to chase aliens, but to expand the space of legitimate inquiry. If 3i Atlas were a technological relic, what would that even mean? It wouldn't have to be a spacecraft in the cinematic sense, no blinking lights or metal skin. It could be a fragment, a shell, a shard of an engineered structure long dormant, something whose material properties are designed, not random, whose surface chemistry confounds our spectroscopy because it was never meant to fit our categories. The absence of dicarbon, the dominance of CO2, the irregular thermal emission, these could, in principle, be side effects of synthetic alloys or metamaterials weathered by eons of interstellar radiation. But physics demands humility. Every one of those same features can also be explained, barely, by natural means. CO2-rich formation in a distant disk, radiolytic processing of organics, plasma-driven quenching of emission bands. The debate, then, isn't about proof. It's about posture. Do we treat the unexplained as noise or as signal? Some argue that the technology hypothesis is less about 3i Atlas itself and more about us. A mirror reflecting our own hunger for pattern in the void. We see precision where probability reigns. We mistake geometry for intent. Perhaps our pattern-seeking minds project meaning onto what is merely chance alignment and exotic chemistry. Yet, as history shows, skepticism without curiosity is just another form of blindness. To explore is not to believe. It is to remain awake to the full spectrum of possibility. When the interstellar visitor Oumuamua slipped by in 2017, its non-gravitational acceleration and lack of cometary tail ignited similar debates. Radiation pressure, outgassing, and fractal shapes were all invoked. Loeb suggested that perhaps we were seeing light sail-like dynamics, not proof of aliens, but a data point too strange to dismiss outright. Now, with 3i Atlas, those whispers return, this time wrapped in a different skin. Chemical anomalies instead of acceleration, photonic mismatches instead of geometry. What if, purely as an exercise in thought, we entertained the engineering hypothesis? What signatures would we expect? Consistent ratios of metals not found in natural objects, coherent radio emissions, heat retention inconsistent with size, precise rotational stability. So far, we see none of those clearly. Yet the mind lingers on the phrase "so far." Because if 3i Atlas were a fragment of something built, its builders would have long since vanished. What remains would be inert, a relic of intent dissolved by time, a technological fossil adrift in interstellar space. The larger lesson here is not about aliens, but about scientific humility. Every discovery that seems absurd at first, radio galaxies, pulsars, quasi-crystals, began as an anomaly someone dared to take seriously. The goal is not to declare, but to notice, to say, "This doesn't fit," and keep watching. The danger isn't that we mistake rocks for machines, it's that we stop asking the question altogether. So maybe the deeper message of 3i Atlas isn't that it is artificial, but that it reminds us how artificial our categories can be. We divide natural from made, alive from inert, signal from noise. The cosmos doesn't. It just moves, reacts, glows, erodes. The green light, the spectral silence, the trajectory, all are part of one performance we don't yet know the script for. Still, as telescopes trace its fading tail, one can't help but wonder, not in fear, but in awe, whether somewhere out there long ago, someone else once looked upon a fragment like this and asked the same question. What if we're not looking at nature but memory? The chemistry of 3i Atlas is abnormal, strong CO2, water, OCS, but missing typical markers like CN. Could it be that some volatile is reacting faster than anticipated? Could hyperoxidation, plasma catalysis, or cosmic irradiation be altering the standard chemical pathways inside its coma? Every comet tells its story through chemistry. Normally, that story is familiar. Sunlight strikes the surface, frozen volatiles sublimate, Radicals form, and their spectral signatures appear in orderly succession. Cn, C2, O, CH, each molecule tracing a step in a well-worn sequence of reactions. But 3I Atlas speaks in a different dialect, a grammar of absence and imbalance. The usual lines are quiet, while others, unexpected and volatile, surge to prominence. Its chemical fingerprint suggests a world where reactions happen too fast, or along pathways that bypass the usual intermediates. CO2 dominates. Water emerges far from the sun. OCS, carbonyl sulfide, appears strong, but Cn and C2 are missing or muted. Something inside that coma is rewiring the logic of molecular chemistry. One theory is hyperoxidation, the idea that an overabundance of oxygen-bearing compounds, perhaps generated by cosmic ray bombardment, is consuming the carbon radicals before they can emit. In that case, carbon atoms liberated from surface ices could be quickly captured into CO or CO2, leaving little free carbon for Cn or C2 to form. The result would be a glow stripped of its traditional carbon chains, chemically clean, but spectrally strange. The comet, in essence, would be oxidizing its own signal away. Another explanation leans on plasma catalysis, a phenomenon in which charged particles accelerate reactions that would otherwise be slow or improbable. As solar wind streams into the expanding coma, it creates a thin, turbulent plasma. Electric fields and electron collisions can excite, ionize, or fragment molecules, turning the coma into a low-density laboratory of exotic chemistry. Under such conditions, radicals form and vanish in microseconds, recombining into species that never stabilize long enough to radiate at predictable wavelengths. The comet's chemistry becomes non-linear, more like lightning in a nebula than sublimation in a freezer. Then there is irradiation, billions of years of exposure to interstellar cosmic rays. Out in deep space, far from any star, high-energy particles slam into frozen molecules, breaking bonds, rearranging atoms, forming complex organic residues known as tholins. Over millennia, these layers accumulate, creating a surface rich in processed carbon and nitrogen compounds, but poor in volatiles. When such a body finally encounters sunlight again, those altered ices don't behave like pristine cometary material. They crack, outgas, and burn in unpredictable ways, releasing strange ratios of gas and dust. It is possible that 3I Atlas is still shedding the chemical memory of that cosmic exposure, a kind of radiation scar written into its composition. There's also the question of temperature gradients. In a typical comet, sublimation zones are well stratified, water near the surface, CO and CO2 deeper down. But in an interstellar object, thermal layering may be inverted or fractured. Tiny inclusions of volatiles may be trapped in carbonaceous matrices that heat unevenly, releasing pockets of gas that recombine before reaching equilibrium. Imagine a labyrinth of microchambers inside the nucleus, each a miniature reaction chamber, each evolving under its own physics. The chemistry we detect in the coma would then be a blended, time-averaged echo of thousands of simultaneous processes, none of them following the rules we expect. When researchers modeled its composition, the implied ratios of CO2 to water, OCS to Cn, were unlike any in their databases. The data resisted fitting. One model could explain the water, but not the sulfur. Another could match the sulfur, but not the missing Cn. Each adjustment produced new contradictions. It was like trying to balance an equation that keeps inventing new terms. What makes this even more confounding is how stable the output seems. Despite its chemical irregularities, 3I Atlas maintains a smooth, continuous glow. No violent outbursts, no fragmenting jets. It is as though the chemical chaos has reached equilibrium, an equilibrium that defies our categories, a stable storm. There's a quiet irony in that. We study comets as time capsules of primordial chemistry, relics of how planets began. But 3I Atlas may not be a time capsule at all. It could be a reaction, ongoing, dynamic, changing faster than we can model it. Its chemistry isn't frozen in time. It's alive in time, rewriting itself moment to moment as it interacts with sunlight, magnetism, and cosmic debris. Whatever is happening inside that coma, hyperoxidation, plasma catalysis, irradiation, or all three, it reveals a simple truth. Chemistry in interstellar space is not static. It evolves, it remembers, it adapts. And perhaps that's the real lesson of 3i Atlas. Not that it breaks the rules, but that it reminds us how narrow our rules have been, written in the language of one small solar system, under one star, with one set of assumptions about how matter should behave. Out there, in the long silence between stars, the chemistry plays by different laws. Suppose inside the coma, a catalyst, metallic atoms, charged particles, trace radicals, is driving rapid recombination. Something that turns carbon chains into excited states that emit green without the standard C2 signature. A chemical anomaly hiding in plain sight. Every chemical reaction has a tempo, a rhythm set by temperature, density, and energy. But what if something inside 3i Atlas is changing the beat, accelerating reactions faster than our equations predict? A comet's coma is supposed to be a slow theatre of physics. Frozen gases sublimate, molecules drift and disperse, sunlight tickles them into brief fluorescence. Yet the data from 3i Atlas suggests something more kinetic, more urgent, as if its chemistry is happening in real time, catalyzed by invisible hands. To understand what might be unfolding there, imagine a cloud where every molecule is charged or excited, a plasma so delicate that a single photon can trigger a cascade of transformations. In such an environment, traditional photochemistry breaks down. Instead of discrete emission lines from familiar species, you get a continuous glow, a spectrum shaped by countless microreactions. Each collision, each recombination, each brief alignment of atoms leaves a trace of light. Not one color, but a field of shifting greens, fading and reforming like breath. In ordinary comets, we know the usual catalysts: ultraviolet light, solar wind ions, energetic electrons from photoionization. But in 3i Atlas, those same agents might be acting on a far more volatile composition. Its coma, dominated by CO2 and trace OCS, is rich in oxygen and sulfur, two elements notorious for their catalytic behavior in plasma environments. When bombarded with solar particles, they can form metastable intermediates that accelerate reactions between carbon fragments and radicals. In effect, they could be turning the coma into a self-sustaining reactor, where the very gases escaping from the surface fuel their own transformation. There's another piece to the puzzle: metals. Polarimetric and infrared data hint at reflective grains mixed into the dust, possibly metallic or mineral in nature. Microscopic specks of iron, nickel, or magnesium could be acting as heterogeneous catalysts, surfaces where reactions happen thousands of times faster than in the surrounding gas. On these tiny platforms, molecules adsorb, rearrange, and release photons as they return to equilibrium. The process is messy, but efficient. 1,000 small reactions for everyone we'd normally expect. In that chaos, it's easy to lose the clean Swan bands of C2, and instead see a diffuse, shifting green. But perhaps the most intriguing catalyst is the comet itself. When a body travels through interstellar space for millions of years, it accumulates a shell of cosmic scars, radiation-altered materials, polymerized carbon, and metallic inclusions formed by micrometeor impacts. Those layers can trap radicals and ions like seeds in amber. When sunlight finally warms them, the bonds snap, releasing not simple molecules but reactive fragments that immediately collide and recombine. The result is a burst of non-equilibrium chemistry, flashes of emission without clear molecular fingerprints. Imagine standing within that expanding cloud. You'd see molecules colliding, shattering, reforming faster than you could measure. There would be no single reaction dominating, no clear pathway, only a living network of reactions feeding on themselves. The green light would not come from any one species, but from the collective agitation of matter, a slow fire burning in a medium too thin to touch. Some researchers have proposed that similar processes occur in planetary atmospheres and auroras, the catalysis of light by turbulence and plasma. On Earth, auroral greens arise from oxygen atoms returning from excited states, energized by charged particles. Perhaps 3I Atlas is producing a cousin of that phenomenon, a cometary aurora, where charged dust and gas interact to create persistent, broadband luminescence. It wouldn't require exotic chemistry, just a different balance of timing and energy, reactions happening faster than their emission spectra can stabilize. If that's true, then the comet's missing C2 lines are not a mystery of absence, but of speed. The molecules form and vanish too quickly to leave their spectral signatures. The green light we see isn't the song of a single molecule, but the blurred chorus of thousands, each singing for an instant before dissolving into the next. A chemical shimmer, not a spectral one. It's tempting to call it chaotic, but perhaps it's more precise than it looks. Maybe this balance between ionization, recombination, and catalysis is the comet's natural equilibrium. A living reaction engine powered by sunlight and shaped by interstellar history. Not broken chemistry, but unfamiliar chemistry. Not a comet misbehaving, but one revealing how diverse matter can be when freed from the narrow conditions of our solar nursery. In that sense, 3I Atlas isn't violating the rules, it's expanding them. It shows that chemistry is not static, even in space. It's a living negotiation between order and energy. And somewhere within that negotiation, hidden behind the green, a new kind of reaction might be unfolding. One we can see, but not yet name. Emissions in comets are often thermal or fluorescent, but non-thermal processes, like charge exchange or auroral-like excitation, could produce odd spectra. Suppose high-energy particles from solar wind or cosmic rays are injecting energy, altering molecular states in unanticipated ways. Every object that enters the heliosphere steps into an invisible storm. The solar wind, streams of charged particles rushing outward from the sun at hundreds of kilometers per second, carries within it an ocean of energy. It's thin, almost ghost-like, but it has the power to reshape the chemistry of anything it touches. When that wind meets a comet, it collides not with solid rock, but with a vast envelope of gas and dust, a boundary between matter and emptiness. In that liminal zone, electricity is born. Normally, the interaction is gentle. Ionized solar particles flow around the coma, charging it, sometimes forming a faint plasma tail. The emission lines that follow are predictable. CO+ glowing blue, Cn shimmering violet, the standard orchestra of ionized gases in sunlight. But 3I Atlas doesn't follow this script. Its coma is behaving as though it's being continually shocked, not thermally, but electrically. One of the first signs of this anomaly was the inconsistency between the optical and infrared data. In thermal emission, brightness is tied directly to temperature. Hotter materials radiate more. But in 3I Atlas, the light intensity fluctuated without corresponding thermal variation. The energy seemed to appear and vanish independently of heat. That is the fingerprint of non-thermal excitation, processes driven not by temperature, but by the direct injection of energy from high-velocity particles. Picture the solar wind slamming into the outer coma. Electrons and protons spiral along magnetic field lines, colliding with neutral gas molecules and knocking electrons free. Some of those collisions create ions that recombine almost instantly, releasing photons in narrow bands. Others elevate atoms to metastable states that radiate as they relax, transitions forbidden in ordinary thermal conditions but made possible by plasma. In this dance, the gas becomes an aurora, not a cold one, not a bright one, but a subtle, invisible glow made of green and red photons, whispering through space. On Earth, We call it the aurora borealis. On a comet, it's stranger, because there's no magnetic field strong enough to shape it, no atmosphere thick enough to contain it. Instead, each molecule becomes its own aurora, its own magnetic bubble. The result is chaotic but beautiful. Patches of emission flickering like candlelight, disconnected yet coherent in pattern. This could explain why 3I Atlas exhibits a smooth, diffuse glow instead of the discrete molecular bands we expect. The glow is not chemical, it's electrical. An orchestra of charged particles playing through a million tiny amplifiers. There's another dimension to this story: cosmic rays. Beyond the solar wind lies an even more powerful storm, the galactic background radiation of high-energy particles that travel through interstellar space. 3I Atlas has spent millions of years adrift in that flux, accumulating charge, embedding ions in its surface, saturating its ices with trapped energy. When sunlight warms it, those ancient ions are released, creating local electric fields. The comet might be discharging like a slow capacitor, releasing bursts of electrons that feed back into the surrounding coma. The boundary between natural plasma and self-generated plasma becomes blurry. The result would be an environment rich in charge exchange, reactions where ions steal electrons from neutral atoms, creating excited states that emit at unusual wavelengths. Laboratory experiments show that charge exchange can produce bright emissions without requiring high temperatures, sometimes even mimicking molecular fluorescence. If this process dominates in 3I Atlas, then the missing spectral fingerprints, the absent C2, the quiet CN, makes sense. Their expected chemical lines are replaced by these ghostly charge exchange lines, broad and shifting, with no stable pattern to identify. It's possible we are witnessing an entirely different kind of light generation, one that sits halfway between chemistry and physics, where matter glows not because it's hot, but because it's charged. If that's true, the green light of 3I Atlas might be an auroral echo, sunlight energizing the solar wind, the wind energizing the comet, and the comet responding in a language of plasma. There is a deeper beauty in that idea. It means the glow we see is not simply emitted, it's participatory. The sun, the wind, the cosmic rays, the dust, all contributing energy, all entangled in the same reaction. The light becomes an ongoing dialogue between star and stranger, and perhaps this is why 3I Atlas feels alive when we watch it. Its luminosity doesn't just come from within, it's a reflection of everything around it, a living exchange between forces that stretch across space. The plasma sings, the ions shimmer, and through it all, the comet drifts onward, carrying that silent voltage like a heartbeat. Nearby, astronomers recently uncovered a vast molecular cloud hidden in green radiation. Could 3I Atlas be passing through a high-energy region that bathes its tail and coma in external fields, altering its emission chemistry? The environment might not be passive. Space is not empty. It hums, it glows, it moves, even in its darkness. Between the stars drift enormous reservoirs of gas and dust, invisible until light or energy passes through them. These are molecular clouds, vast, cold nurseries of future suns. But sometimes they are not as dormant as they seem. Radiation, shock waves, or magnetic turbulence can awaken them, charging their particles, making them emit light in colors that shouldn't belong to the void. And lately, telescopes mapping faint optical emissions near our solar neighborhood have revealed something unsettling: a diffuse, greenish radiation seeping across the background. Some astronomers suspect that this region, still unnamed and barely charted, could be an ancient molecular cloud, one that lies on the very edge of our local bubble. Not dense enough to form stars, but still rich with carbon, oxygen, and ionized metals drifting in a low-energy plasma. And by chance, 3I Atlas is moving through its fringe. If that's true, the comet isn't glowing in isolation. It's being illuminated, excited not just by sunlight, but by the invisible rain of high-energy photons, electrons, and ions from the cloud itself. The green color we see, the strange polarization, even the non-thermal emission patterns could all be partially external, the cosmic equivalent of a shadow being backlit by lightning. The cloud could be bathing 3I Atlas in an electromagnetic fog, subtly rewriting the energy states of the molecules in its coma. Imagine it, a foreign body from another star system passing through the residue of a dead stellar nursery. Ancient chemistry meeting ancient chemistry, each reacting to the other in real time. The comet's CO2-rich gases, already volatile, would find themselves immersed in an ionized medium filled with free electrons and excited hydrogen. Those particles could collide with the expanding coma, triggering charge exchange emissions that mimic fluorescence. The resulting light wouldn't depend solely on what's inside the comet, but on what surrounds it. This could explain why the glow of 3I Atlas appears inconsistent across wavelengths, or why its brightness sometimes fluctuates independently of its distance from the Sun. Its illumination might not be controlled by internal sublimation or thermal activity alone. It might be driven by the changing density and energy of the region it's passing through, the way a ship at sea gleams brighter when it crosses into bioluminescent waters. There's evidence to suggest the solar system is entering a more active region of the interstellar medium, the boundary between our local bubble and denser interstellar filaments. Astronomers have traced hydrogen emission maps showing a slow rise in background ionization. If 3I Atlas is riding through that transitional space, its coma would be immersed in a flux of external excitation, unlike anything encountered by typical comets born within our solar system. It's a reminder that the sky around us isn't a static backdrop. It's a moving, reactive medium. If the molecular cloud is even slightly magnetized, its fields could interact with the comet's ion tail, twisting it, inducing currents, maybe even generating local auroras. This could produce polarized light variations and subtle oscillations in brightness, exactly what some observatories have recorded. In that sense, 3I Atlas isn't just glowing, it's resonating with its surroundings, the way a string vibrates when brushed by air. And maybe that's why the chemistry seems inconsistent. The comet's interior is providing one source of emission, while the interstellar environment adds another, both overlapping in frequency, both shaped by fields we can't yet fully map. To our instruments, it looks like a mismatch, but to the cosmos, it's harmony. Two systems, one transient, one eternal, momentarily intersecting and exchanging energy. When we think of space, we often imagine isolation, objects adrift in a vacuum, untouched and unchanging. But reality is messier. Everything that drifts through the galaxy interacts with something. Fields, winds, radiation, invisible tides that press against every atom. 3I Atlas is simply the latest traveler to remind us that no journey through the stars is ever truly solitary. The environment isn't passive, it listens, it answers, and when the right traveler passes through, it glows. Observers are noting that the green emission emerges sharply at certain heliocentric distances, suggesting a threshold or switch. Below a temperature, nothing happens. Above it, something ignites. This threshold behavior is more consistent with phase transitions or activation energies than with gradual sublimation. There is something strange about the way 3I Atlas awakens. For weeks, it drifts in silence, dark, unreactive, distant. Then, as it crosses a specific point in its orbit, the transformation begins almost instantly. The coma expands, the surface brightens, and that elusive green signature flares into existence. It doesn't ramp up slowly like a normal comet. It switches on, as though triggered by a hidden mechanism waiting for a particular cue. In the language of chemistry, this kind of behavior points to an activation threshold, a precise balance of temperature and pressure at which a dormant process suddenly becomes self-sustaining. It's the same physics behind combustion, crystallization, or phase changes. Below the threshold, the energy input isn't enough to overcome the reaction barrier, but once the critical point is reached, the system reorganizes and everything changes at once. For most comets, sublimation is gradual. Water ice begins to vaporize gently at around 180 K, driving a steady outflow of gas and dust that strengthens as the Sun approaches. But 3I Atlas seems to defy this logic. Its activity doesn't follow the smooth curve of solar heating, it leaps. Below a certain temperature, the coma remains chemically inert. Above it, a cascade begins. Something inside is undergoing a phase transition. Perhaps the crystallization of amorphous ice, or the release of trapped gases from within micropores. When amorphous water ice reorganizes into a crystalline structure, it releases latent heat, enough to drive rapid sublimation and even explosive venting. That could explain the sudden outgassing of CO2 and the abrupt onset of green light. Yet the precision of the threshold is what makes it so intriguing. It's as if the internal composition of 3I Atlas has been engineered by temperature itself. Layers of different ices stacked in perfect sequence, each with its own ignition point. First, the outer frost evaporates. Then, when the Sun's energy reaches just the right depth, deeper materials begin to react. The CO2, the water, the sulfur compounds, each responding at their own critical temperature. The result is not a smooth fade-in, but a series of distinct awakenings. This stepwise activation could explain why the comet's emission lines appear and vanish unpredictably. At certain distances, CO2 dominates. At others, water takes over. And in between, at that narrow thermal window, we see the green flare, uncorrelated with either. Perhaps that's the moment when a particular reaction becomes possible. Oxygen reacting with carbon radicals, or plasma recombination occurring efficiently only within a certain temperature range. Once the comet passes beyond that zone, the chemistry resets. There's also a mechanical aspect. As heat diffuses inward, gases trapped in subsurface cavities can expand until pressure fractures the crust. When the crack opens, a jet of material erupts, spewing dust and ice into the coma. The sudden exposure of fresh, volatile, rich material could create a localized burst of emission, a flash that briefly dominates the comet's visible light before fading. In this way, the switch is both chemical and structural, a feedback loop between temperature, pressure, and release. It's worth considering that these thresholds might not be purely thermal. They could be electrochemical. As sunlight and solar wind charge the surface, voltage differentials can build between the nucleus and its coma. When the electric field reaches a critical value, a discharge occurs, micro-arcs that momentarily energize nearby gas molecules, producing short-lived emission spikes. In that sense, the ignition point isn't just about heat, but about charge, a flicker of electricity setting off a chemical chain reaction. From a distance, these processes merge into a single observation. The green light appears only when the comet crosses an invisible line in space. Below it, stillness. Above it, fire. Like a celestial transistor switching states, 3I Atlas alternates between silence and brilliance, governed by laws we're only beginning to perceive. What makes this all the more mysterious is how reproducible it seems. Independent observatories, tracking from different vantage points, report the same thresholds at nearly identical solar distances. This suggests the effect isn't random or observational, it's intrinsic. The comet itself remembers its temperature, carrying within it the memory of its own ignition point. There's a strange kind of elegance to that. The idea that an object from another star system, cold, ancient, alien, could carry within it a built-in trigger, a precise boundary between inert and active, dark and luminous. It means that somewhere inside its layered shell, physics and chemistry conspire to perform the same simple act the cosmos performs everywhere, transformation at the edge of stability. Every reaction, no matter how complex, begins this way, a quiet build-up of potential, a moment of equilibrium, then the tipping point. 3I Atlas is showing us that even in the deep cold of space, nature still knows how to build tension, how to hold its breath, and then, with exquisite timing, let go. Spectroscopic shadows, Absorption lines that should darken a region are missing. Even in parts of the coma with cooler gas, we don't see expected absorption. That implies the gas is either fully excited, optically thin, or undergoing continuous transition. The whole cloud seems alive, not static. It's one of the most subtle clues, and one of the most revealing. When light passes through a cloud of gas, we expect it to bear the marks of that journey, fine absorption lines carved out of the spectrum like fingerprints pressed into glass. Every element, every molecule steals a tiny piece of light at precise wavelengths. These dark notches, those shadows, are the language of matter itself. But in the case of 3I Atlas, that language is missing. Even in regions of the coma where gas density should be high and temperatures low, the expected shadows never appear. The continuum is smooth, eerily smooth. No absorption troughs, no structured dips, no contrast between bright and dim. As if the gas isn't merely transparent, but luminous all the way through. The light isn't passing through the coma is the light. That absence is deeply unorthodox. It tells us that the gas is not in a steady state of equilibrium, where some molecules absorb while others emit. Instead, everything appears to be excited, dynamic, in motion. Each molecule is being nudged, energized, and re-excited before it ever has the chance to rest. It's as if the entire environment is in a state of constant transition. No stillness, no shadow, just flux. This could mean several things. The first possibility is that the coma is optically thin, so sparse that the photons don't interact with enough material to carve shadows at all. But that doesn't align with the brightness data. The emission is too strong, the scattering too intense. The coma is clearly rich in gas and dust. So perhaps it's the opposite. Optically thick, a region so saturated with emission that any absorption is immediately filled back in by re-emission. In that case, every photon lost is instantly replaced by another born in the same wavelength, creating a self-healing light. Another explanation is continuous excitation, a state where molecules are constantly being energized faster than they can decay. If the excitation rate exceeds the relaxation rate, there's never time for absorption to leave a mark. Each molecule that captures a photon re-emits almost instantly, erasing its own shadow. This is not the calm fluorescence we're used to. It's a rolling storm of molecular energy exchange, like a chorus of overlapping notes that never resolve. It's also possible that the light we're seeing is dominated by non-thermal processes. In plasma environments, electrons and ions collide at random energies, creating emissions that don't conform to thermal distributions. The result is a smooth, continuous spectrum with few distinct lines. Precisely what we see. If the coma of 3I Atlas has become partially ionized, its light might be governed less by temperature and more by electric potential. In that regime, the idea of shadows ceases to apply. But there's another, more poetic interpretation. The gas might be illuminated from within. If the coma is producing its own internal emission through chemical reactions, plasma instabilities, or the slow release of trapped energy, then it's glowing not because of external sunlight, but because of its own internal physics. The light doesn't just pass through, it's born in every cubic meter of the cloud. 1,000 invisible lanterns, all burning at once. From a distance, it gives the coma an uncanny look. Observers describe it as soft, almost gelatinous, not sharply bounded, not opaque, but self-luminous. The green fades gently outward, instead of being cut off by a sharp edge. That gradient is the signature of a process that's ongoing, diffuse, and distributed. A field, not a surface. It's unsettling in a way, to see an object that refuses to cast or receive its own shadows. It means we're looking at a region where equilibrium, the backbone of most natural systems, doesn't exist. Every molecule of gas is both emitter and absorber, both subject and source. It's a physics of constant renewal, where the distinction between light and matter begins to blur. In such an environment, the notion of a line spectrum, neat, identifiable, taxonomic, begins to dissolve. What's left is something more fluid, more organic. The coma becomes less a structure and more an event, a living system of exchange where energy moves like thought, invisible but ceaseless. And perhaps that's why 3I Atlas feels so alien. Not because it's foreign in origin, but because it operates in a state we rarely witness. A system that doesn't reflect the light of the universe, but participates in it. It's a reminder that not all illumination comes from contrast. Not all truth comes from shadow. Some things glow because they never stop moving, because they never rest long enough to dim. The whole cloud seems alive because, in a very real way, it is. A self-stirring plasma, a chemical ocean where matter and light are indistinguishable for a fleeting moment. And as it drifts onward, we realize, perhaps this is what life looks like on a cosmic scale. Not biology, but perpetual excitation. Where does the energy come from? If we estimate the photon output required to power this glow, classical sublimation and solar heating may not suffice. We may need an internal heat source, radioactive decay, or even stored chemical potential. Can a coma sustain spontaneous glowing apart from solar input? Every photon has a cost. When something glows, something must pay for that light. In heat, in motion, in the rearrangement of bonds. For most comets, the bill is footed by the sun. Sunlight warms the nucleus. Ices sublimate. Gases expand and fluoresce. The energy flow is straightforward, balanced, predictable. But with 3I Atlas, the math doesn't work. The intensity of its glow, the persistence of its green emission, and the smoothness of its spectral output all suggest an energy budget larger than what solar radiation alone could provide. If you treat the coma like a standard radiating body, account for its cross-sectional area, albedo, and distance from the sun, the available solar energy falls short by a factor of several. Too dim a star, too far a reach. Yet the comet continues to glow as though powered from within. That forces us to consider something more complex. Internal or non-solar sources of energy, quietly fueling the light from beneath the surface. The first possibility is latent heat, energy stored in phase transitions. When amorphous ice transforms into crystalline form, it releases heat, enough to drive localized sublimation and even sustained outgassing long after direct sunlight fades. The process can cascade. One region crystallizes, warms another, triggers further transitions. It's not a continuous furnace, but a chain reaction of tiny awakenings, each one releasing just enough warmth to keep the coma alive. A slow burn frozen inside an interstellar shell. But latent heat alone may not explain the steadiness of the emission. That brings us to a more exotic candidate, radiogenic energy. In the earliest days of planetary formation, radioactive isotopes like aluminum-26 and iron-60 were common. Their half-lives are short, but if 3I Atlas formed around a younger, more active star, it could still contain long-lived isotopes, uranium, thorium, potassium-40, trace amounts of which can generate internal warmth for billions of years. On Earth, that energy powers the movement of continents. Inside a comet, it could be enough to prevent total freezing, keeping volatile materials just mobile enough to react when disturbed. Then there's chemical potential, the quiet storage of imbalance. Over eons of cosmic irradiation, ices can become chemically charged, forming unstable compounds like peroxides or trapped radicals. When these materials thaw or collide, they recombine exothermically, releasing bursts of energy. Laboratory analogues show that even small concentrations of such compounds can power sustained luminescence in vacuum chambers. The energy is subtle but cumulative, like a forest of microscopic sparks. Perhaps what we're witnessing in 3I Atlas is a combination of these sources, synchronized into a feedback loop. A small injection of solar heat triggers the release of latent heat, which in turn drives localized chemistry. The chemical reactions free stored energy, producing photons, which then further heat the dust and gas, sustaining the cycle. Each photon emitted isn't the end of the process, it's a sign of the next one beginning. The comet becomes a self-fueling system, not perpetual, but persistent, balancing between exhaustion and renewal. That model would also explain the smoothness of its emission. In thermal systems, fluctuations are noisy, they spike and fade. But in self-regulating chemical systems, the glow stabilizes, like embers smoldering at equilibrium. It's the signature of balance, not chaos. Of course, there's the final, stranger possibility that the energy isn't coming from within the comet at all, but from interactions at its boundary. As it moves through charged regions of space, the comet's plasma sheath may act as a capacitor, accumulating electric potential from the solar wind. When the charge differential reaches a certain point, discharges occur, micro-arcs invisible in ordinary light, but strong enough to excite surrounding gases. If that's happening continuously, then the coma's energy source is not chemical or thermal, but electrodynamic. The light we see would be the side effect of a circuit closing across millions of kilometers. Whichever explanation proves true, the implication is profound. 3I Atlas isn't a passive reflector of sunlight. It's an active participant in its own illumination. Its glow isn't simply borrowed from the sun. It's the product of ancient energy reserves, unlocked through chemistry, radioactivity, and plasma exchange. That realization blurs one of the oldest distinctions in astronomy, the line between what shines and what reflects. Most things in our solar system are lit from without. Only stars shine from within. But 3I Atlas sits uneasily between the two, neither inert nor self-luminous in the stellar sense, but something in between, something hybrid. It glows because energy, stored across epochs, is being spent before our eyes. Maybe that's the truest form of light, not radiance born from fusion, but the slow release of memory. Energy once locked in matter, finally let go after a million years of silence. 3 Atlas shines because it remembers what it's made of. In radio astronomy, one of the most striking mysteries in recent years has been the fast radio bursts, FRBs. Bright, ultra-short pulses of radio emission that seem to come out of nowhere, lasting milliseconds, yet radiating enormous energy. Some appear only once, others repeat in irregular patterns. They violate expectations. They demand new thinking. What if 3I Atlas is something like an optical analog of an FRB, not a sudden pulse in the radio, but a sustained anomalous glow in visible green light? To compare helps sharpen the strangeness of what we actually observe. FRBs come in two broad classes: one-off events, seemingly singular, and repeaters, active over time, flickering, bursting, or going silent, then returning. The statistical differences between them are real. Repeaters tend to show wider pulse widths, more complex spectral structure, and often exist in particular host environments. One-off FRBs tend to have higher peak luminosities in single bursts and are often harder to localize and study. If 3I Atlas is broadcasting green light instead of radio pulses, it is doing so with neither the brevity of an FRB nor the manic repetition. Its glow is persistent, or at least sustained over days, weeks, not millisecond bursts. Yet it shares something else: spectral anomalies, behavior that doesn't fit within standard emission models. Just as repeaters challenge the idea that every FRB can be explained by a single mechanism, 3I Atlas challenges the idea that every comet must obey the same chemical and spectroscopic rules. Consider the way we see FRBs sometimes associated with external magnetic fields, strong Faraday rotation measures, complex polarization, delays, scattering, varied bandwidth, sometimes periodicity. In 3I Atlas, we see unusual polarization curves, dust behavior that diverges from known norms, spectral holes, missing signatures like C2, Cn, that resemble the way FRB spectra sometimes suppress or mask expected emission at certain frequencies. Maybe the analogy is loose, but it's a useful mirror. What if the green glow is a burst stretched out in time, a continuous but variable emission instead of a flash? Another point, in seeking optical counterparts to FRBs, astronomers have often come up with null results, but in a few cases, there are candidate optical transients tied to known repeaters. These are faint, low confidence, sometimes coincident in time or space. They show that non-radio light can sometimes accompany or follow FRBs, but that those signals are rare or smeared out or hard to isolate. If 3i Atlas is acting like an optical counterpart to something akin to FRBs, it suggests that perhaps there is a class of objects whose emission bridges wavelengths, radio, UV, visible. Perhaps the unusual chemistry, plasma processes, and catalytic interactions we've already discussed act like a low-frequency extension of the extreme conditions that produce FRBs. Rather than a brief broadband radio, flash, we might have a slow, persistent green luminescence, maintained by comparable energetics, but smeared out temporally by the physical scale of the coma, by the low density, by continuous excitation, rather than one-off events. Statistically, what would that mean? It would require that astronomers detect many more objects like 3i Atlas glowing in green, behaving in similar anomalous ways, to see whether they cluster in space, distance, composition, or trajectory. If only one appears, it might be a fluke. But if a population emerges, then the FRB analogy becomes more than metaphor. It becomes a guide to a new phenomenon. Slow optical bursts, or persistent emission anomalies in interstellar objects. In short, comparing 3i Atlas to FRBs highlights both divergence and possible convergence. Divergence. 3i Atlas is not impulsive, not radio, not short. Convergence. It shares the deep anomalies in spectrum, in energy balance, in behavior outside expectations. Those shared features push us to ask, is the cosmos richer, more varied, in how and where it makes light than we imagined? And that is what makes this comparison important. Not to conflate 3i Atlas with FRBs, but to use FRBs as a mirror, exposing what is strange and what might be possible. Because when phenomena in radio break our theories, maybe phenomena in visible light are doing the same. Just more slowly, just more quietly, but no less real. We expect markers, specific spectral lines, isotope ratios, radicals, but time and again, they're absent or suppressed. This absence is meaningful, not emptiness, but hidden structure. Science sometimes learns more from what doesn't appear than from what does. Every observation is a conversation with silence. We shine light on the universe and wait for it to answer. In photons, in echoes, in patterns that match what we know. But sometimes, the silence itself speaks louder. With 3i Atlas, what haunts astronomers isn't what they see, but what they don't. Across multiple instruments, optical, ultraviolet, infrared, the expected signatures remain stubbornly missing. No Swan bands of C2, no CN radicals. Even isotopic ratios that should emerge in the infrared remain blurred, smoothed away, as if erased. The data looks incomplete, but it isn't. It's just too clean. Like a sound recording with the background noise surgically removed. The melody remains, but it's disembodied, unnatural in its perfection. In spectroscopy, absence is never neutral. When lines vanish, it's because the medium refuses to let them form. Either the transitions are being quenched, the gas is too excited to absorb, or the conditions are so turbulent that distinct features blur into a continuum. Each missing line is a clue about the state of matter, its density, its temperature, its symmetry. And so, the very emptiness of 3i Atlas's spectrum becomes a kind of signature in itself, a negative imprint. There's precedent for this kind of mystery. Astronomers studying the interstellar medium once stumbled on diffuse interstellar bands, broad absorption features that resisted identification for nearly a century. They weren't defined by what they were, but by what they weren't. For decades, no molecule could explain them, until complex carbon chains and fullerenes were finally proposed. 3I Atlas might be offering a similar challenge, a new kind of diffuse signature, one that hides its detail beneath too much motion, too much energy, too much light. It's tempting to think of absence as lack, but in systems out of equilibrium, absence is often abundance disguised. A saturated plasma, for instance, can mask emission lines entirely. A turbulent gas cloud can blur isotopic distinctions until they dissolve into a single continuous glow. The missing spectral structure of 3I Atlas might not signal emptiness, but activity, a state so energetically complex that our instruments, tuned for calm skies, cannot disentangle its threads. Another possibility is geometric. If the coma is optically thin but spatially structured, filled with gradients of temperature and density, photons from different regions could overlap destructively, cancelling out narrow features. The result would be a smoothed spectrum with faint ripples instead of sharp peaks. The information is still there, just hidden in phase, the way interference can silence a sound while preserving its presence. And then there's the more philosophical reading. Maybe what we're calling absence is simply the limit of our attention. Every instrument has a sensitivity curve. Every theory has blind spots. We look for C2 and Cn because that's what our models tell us to expect. But what if 3I Atlas is rich in compounds we don't yet have names for? Metastable carbon oxides, exotic organosulfur species, or radicals formed under interstellar radiation never before measured in a lab. Their lines could fall outside our observation bands, or blend together into signals we've misclassified as noise. The danger of science isn't in being wrong, it's in assuming completeness. The spectrum of 3I Atlas humbles that assumption. It tells us that even in the age of super telescopes and cryogenic spectrometers, the universe can still withhold its details. It reminds us that discovery often comes not from the lines we can plot, but from the spaces between them. Maybe that's why this absence feels so deliberate, because when something from beyond our solar system drifts past, glowing in a way that shouldn't exist, and it refuses to reveal its chemical name, the silence becomes almost personal. The data isn't empty, it's encrypted, and so, the signature we never see becomes the story itself. The missing lines, the blurred ratios, the vanishing radicals, they are the footprint of a system not hiding, but operating in a state we haven't yet learned to describe. The universe isn't withholding meaning. It's inviting us to invent a new language to find it. One theory, an exotic carbon allotrope or radical, not C2 but something like C4 or charged carbon clusters, is producing green emission in unfamiliar bands. The internal conditions of the coma might favor these over traditional diatomic species. In other words, we may be viewing a new branch of comet chemistry. When astronomers first noticed the green glow of comets in the 19th century, they didn't yet know the source. It wasn't until the early 20th that the Swan bands of diatomic carbon, C2, were identified as the culprit. Since then, that association has been nearly axiomatic. Green light means C2, but 3I Atlas has broken that rule. The glow remains, but the fingerprint is gone. And that means the chemistry, the very architecture of carbon in its coma, might be rewriting itself. The leading idea is that under the unique physical and radiative conditions around 3I Atlas, carbon may not exist primarily as simple diatomic molecules. Instead, it could be clustering, forming larger chains or radicals like C3, C4, or even ionized carbon networks. These clusters are transient and difficult to detect because their spectral signatures overlap or shift depending on temperature, charge, and geometry. They exist at the edge between chemistry and plasma, a realm where bonds are constantly forming and breaking. In laboratory plasmas, when carbon-rich gases are bombarded by ions or UV light, something similar happens. Instead of clean C2 emission, the system produces a mixture of linear and cyclic carbon clusters, each with its own brief, unstable emission bands. Some of those bands fall in the green, particularly around 515 to 540 nanometers, right where 3I Atlas glows. That's not coincidence. It's the same chemistry, but on a cosmic scale, where solar radiation, particle flux, and cryogenic temperatures create conditions no Earth-based lab can sustain. The key lies in balance, or rather, in its absence. Inside a normal comet's coma, equilibrium favors smaller molecules, C2, Cn, Ch. But 3I Atlas isn't in equilibrium. Its environment is too dynamic, too charged. UV photons and cosmic particles are constantly striking the surface, creating bursts of reactive fragments. In such an environment, carbon radicals may never settle into C2 before being driven into new configurations. Larger clusters might be momentarily stabilized by surrounding CO2 or sulfur-bearing gases, then disrupted again. A molecular carousel, spinning faster than our spectrometers can resolve. If these transient carbon chains dominate, their emission spectrum would look very different from the textbook Swan bands. Instead of distinct peaks, we'd see a smeared plateau of green, diffuse, continuous, and featureless to the eye. Exactly what we observe. This could explain why attempts to isolate the characteristic C2 pattern have failed. The signal is being drowned out by a swarm of neighboring bands from larger carbon species. Some researchers have even suggested that the glow could arise from Rydberg matter, exotic aggregates of excited atoms bound together by their high-energy electrons. In theory, such states can form in low-density, cold environments exposed to UV radiation. They exhibit broad, non-linear emission spectra, often centered in the visible. If 3I Atlas hosts such exotic carbon matter, it would represent not just a new kind of cometary chemistry, but a new phase of matter existing naturally in space. The implications ripple outward. Carbon, the backbone of organic chemistry, is astonishingly adaptable. On Earth, it builds life. In space, it builds soot, graphite, fullerenes, and dust. If 3I Atlas is revealing a new stable form of carbon aggregation, one that glows instead of absorbs, it could expand our understanding of how carbon evolves between stars. Perhaps these clusters serve as intermediates in the formation of the larger carbonaceous grains found throughout the interstellar medium. There's beauty in that thought, that what we're witnessing might not be alien at all, but ancestral. A glimpse of carbon in the act of becoming, chemistry in transition, caught between molecule and mineral. And yet, it's also humbling, because even if we can model the emission, even if we reproduce it in a lab, it means we've just scratched the surface of what carbon can do under extreme conditions. The element we thought we knew, the element of our bodies, our planets, our words, may still hold phases we've never seen, existing quietly between stars. So when 3I Atlas shines green without C2, maybe it isn't breaking the rule. Maybe it's reminding us that the rule was never complete. Another theory, subsurface heat, perhaps from radioactive material or trapped isotopes, is driving internal reactions. These reactants escape not just as simple volatiles, but as intermediates that glow when they decouple. In this sense, the comet is processing its own matter in real time. Deep beneath the visible frost of 3I Atlas, something may be stirring. Not just sublimation, but reaction. While the surface interacts with sunlight, the interior could be conducting its own slow alchemy, a chemistry fed by ancient energy sealed within. The nucleus of an interstellar object is not a uniform block of ice and rock. It is a labyrinth of pockets, pores, and trapped compounds accumulated over millions of years. In that darkness, heat, even faint heat, can become an architect. If small amounts of radioactive isotopes remain embedded in the core, remnants of its birth in another stellar nursery, they could generate a steady, imperceptible warmth. Not enough to melt or boil, but enough to shift molecular bonds, to drive reactions that wouldn't otherwise occur in the cold vacuum of interstellar space. The heat seeps outward, awakening trapped radicals. freeing oxygen, carbon, and sulfur from their crystalline cages. What escapes to the surface is not inert gas, but half-finished chemistry, intermediates, charged fragments, molecules in motion. When those intermediates meet the vacuum, they collide, recombine, and decay, all within the diffuse exosphere of the coma. The result is light. Not reflected sunlight, not standard fluorescence, but a kind of chemical luminescence. Molecules releasing their stored energy as they break apart. In that view, 3I Atlas isn't just venting, it's metabolizing. Its green glow becomes the visible trace of matter reorganizing itself, atom by atom, reaction by reaction. If that sounds fanciful, it isn't without precedent. Laboratory studies of irradiated ices, mixtures of CO2, H2O, CH4, and organics show that trapped radicals can persist for centuries at cryogenic temperatures. Once gently heated, they react explosively, producing transient emission lines and molecular fragments not seen in equilibrium conditions. On 3I Atlas, the same process could be scaled up 1,000,000-fold. Each fissure on its surface, a miniature reactor, each plume a momentary flare of recombination. This could explain the otherwise puzzling smoothness of the comet's light curve. Instead of chaotic bursts driven by external sunlight, its activity might be sustained internally, the result of distributed chemical energy gradually leaking to the surface. As one region cools, another ignites. The system regulates itself, balancing heat production and release like a slow-beating heart. To an observer, it would appear constant, even serene. To the molecules inside, it would be anything but. Subsurface catalysis might also play a role. If metallic grains or mineral inclusions exist within the nucleus, nickel, iron, silicates laced with trace elements, they could serve as catalytic surfaces. As trapped gases diffuse through the porous interior, these catalysts would accelerate recombination reactions, producing both heat and light. It's a feedback loop. Chemical energy drives heat, heat drives further reaction, and each reaction feeds the next layer outward. At the atomic level, the glow we see could be the afterimage of countless such reactions unfolding in the invisible spaces between dust and ice. CO2 molecules breaking into CO and O, oxygen radicals colliding with carbon chains, reassembling into something momentarily stable before flying apart again. Each cycle leaves behind a photon, a green one in this case, before vanishing into the void. If true, this would make 3I Atlas the first observed case of autocatalytic outgassing, a body generating sustained chemical light from within, not just through solar stimulation. That alone would redefine how we think about cometary evolution. No longer simple relics of formation, such objects could be dynamic, self-processing systems, slowly altering their own composition as they drift between stars. And what's more, this process could persist for eons. Even a small amount of radioactive material, potassium-40, uranium-238, thorium-232, would be enough to maintain subcrustal warmth over billions of years. When the comet approaches a new star, that residual heat joins forces with external radiation, reawakening reactions that never fully ended. 3I Atlas becomes a traveler not just between systems, but between epochs, a body carrying chemistry from its birthplace into every stellar neighborhood it passes through. So perhaps what we're witnessing isn't an anomaly at all, but a glimpse into an ongoing story. Matter learning to rearrange itself under the quiet hand of entropy. The glow, then, is not a mystery to solve, but a heartbeat to witness. The faint green light is energy returning to the cosmos in its most honest form. The release of what was once stored, the soft exhalation of a world remembering how to change. A more daring scenario: what if parts of the nucleus are engineered or altered, maybe via ancient nanostructures, catalytic lattice networks, that modulate emission when solar input triggers them? I'm not saying this is likely, but it remains within the edge of plausible domain. There's a boundary in science, faint, controversial, but necessary, between what we know nature can do and what it might one day reveal it has already done. 3I Atlas lives right on that boundary. We can explain most of its behavior through chemistry, plasma, and physics, but some patterns feel deliberate, repeating polarization alignments, emission thresholds that behave more like digital triggers than gradual reactions, temporal periodicities too stable for chaos, too subtle for coincidence. If we allow ourselves, carefully, to step to the edge of plausibility, another hypothesis appears. What if the comet's nucleus contains structure, not random mineral veins or fractures, but ordered frameworks that influence its energy output? Not conscious machines, but architectures of matter arranged in ways that amplify or modulate chemical and electromagnetic responses. Catalytic lattices, photonic crystals, or nanostructures built long ago by natural processes, or perhaps something older still, something intentional. To entertain such a possibility isn't to drift into fantasy. It's to acknowledge that engineering doesn't have to mean metal. Nature itself engineers with carbon, silicon, ice, and time. Think of opals, of radiolaria, of the layered latticework inside a butterfly's wing. All natural photonic systems that manipulate light with atomic precision. If such structures can form on Earth through slow, biological, or geological self-assembly, why not in the interstellar dark, where radiation, pressure, and magnetism have billions of years to sculpt order from chaos? Suppose the nucleus of 3I Atlas harbors regions of structured carbon, perhaps graphitic networks, or nanostructured ice riddled with metallic inclusions. When sunlight or charged particles strike those lattices, the material could respond in quantized ways, electrons excited along specific geometric paths, emission resonating at distinct wavelengths. Instead of a continuous spectrum, you get modulated light, flickers, polarization shifts, even pseudo-periodic brightening. To an observer, it might look like information, or at least intention. We've seen primitive analogues of this on Earth. Certain minerals under stress emit coherent phonons and light pulses, piezoluminescence. Nanostructured surfaces can trap photons and re-emit them at tuned frequencies. Even simple catalytic networks can switch chemical states in response to thresholds of energy, creating rhythmic oscillations that resemble computation. If 3I Atlas contains such naturally or artificially arranged domains, they could function as cosmic transistors, opening and closing emission channels as the solar wind sweeps across them. The idea stretches our definitions, but not beyond breaking. Because engineering, in this cosmic sense, might not mean design in the human way, blueprints and purpose, but selection. Structures that persist because they interact efficiently with energy. Over countless eons, only the most stable, resonant configurations survive. What emerges may look deliberate, but it's simply evolution extended to materials, self-organization at the scale of atoms and fields. Still, there's a haunting symmetry to it. A body built, or self-built, to glow only under certain conditions. To store potential in its structure, then release it when bathed in starlight. That would make 3I Atlas not just a rock or relic, but a kind of interstellar recorder. A vessel whose brightness is a byproduct of its architecture. Could that architecture be artificial in origin, remnants of an ancient civilization's materials, long eroded, carried across light years? Possibly, though probability leans heavily against it. Yet the notion serves a deeper purpose. It asks us to look for structure, for order, even in chaos. To remember that not every engineered thing must be built by hands. If, by some extraordinary chance, the nucleus of 3I Atlas does contain patterned materials, nanocrystals, metallic veins, self-assembling films, then its behavior makes sense. The sharp activation thresholds, the stable emission harmonics, the repeating polarization signatures, all could arise from structured interactions between light and lattice. The comet wouldn't be a machine, but it would act like one, converting incoming energy into patterned output. And perhaps that's the most compelling vision of all, not a spacecraft, but a structure of memory. A thing shaped to remember energy, to respond when light finds it again after 1,000 millennia of darkness. Whether born from nature or something else, it would stand as proof that form and function are universal languages, older than us, written in atoms and time. Maybe that's what 3i Atlas really is, a vessel that was never meant to communicate, only to resonate. A body so precisely built by physics or by chance that when sunlight touches it, it sings. If our theories hold, we should see telltale signs, transient flickers, shifts in line ratios with distance, polarization changes over hours, abrupt spectral jumps as thresholds cross. Future IR and radio telescopes should detect companion emissions or non-linear coupling with other wavelengths. Every mystery invites its own experiment. For all our speculation about what 3i Atlas is, chemical reactor, plasma phenomenon, self-structured relic, the sky itself will answer in the language of light and time. The predictions are clear, even if the explanations are not. If the glow we see is governed by thresholds, catalysis, or structured emission, then it should behave with precision, not randomness. The universe rarely hides its mechanics. It only asks that we look long enough to see the rhythm. The first thing to watch is flicker, the subtle breathing of brightness over short timescales. Not tumbling rotation, not random outgassing, but micro-variability, millisecond-to-minute fluctuations in green intensity. These would betray processes driven by energy feedback, localized regions heating, cooling, and reigniting in response to passing solar particles. Instruments capable of rapid photometry could capture this heartbeat. If the light is chemical, the flicker will be chaotic. If it's structured, it will repeat. Next are line ratio shifts, small changes in the relative strengths of emission features as the comet's distance from the Sun evolves. In conventional comets, such ratios change smoothly with temperature. But in 3i Atlas, we'd expect sudden breaks, the spectral equivalent of a switch flipping on and off. If the green emission is tied to activation thresholds or internal chemistry, the transition will be discrete. Cross one distance, the light blooms, cross another, it fades. Mapping these transitions could give us the first functional temperature curve of an interstellar chemical system. Polarization offers another clue. As the comet rotates, the scattering geometry of its dust changes. But in 3i Atlas, the polarization doesn't just depend on viewing angle, it pulses. Observers have already noted polarization drops at low phase angles, suggesting unusual dust composition or electric field alignment. If those alignments are being modulated by plasma or internal structure, we should see small periodic oscillations, polarization signatures that evolve on the timescale of hours, not days. That would hint at coherence, an interaction between dust grains and magnetic fields that's active, not passive. The most dramatic prediction lies in spectral jumps. If the emission is driven by reaction thresholds or subsurface heat pulses, then as 3i Atlas warms, new species should appear abruptly, not gradually, a sudden spike in CO2 lines, a brief appearance of CH or OI at specific heliocentric distances. These discontinuities would mark the ignition points of buried processes, the precise moments when chemistry reorganizes itself into light. Beyond the visible, the key will be in the infrared and radio. If the coma's green glow is connected to non-thermal excitation, then other wavelengths must be whispering alongside it. Weak infrared continuum variations, perhaps correlated with optical pulses. Sub-millimeter radio lines, fluctuating in tandem with brightness. These could reveal coupling between molecular transitions, light in one band triggering emission in another. The effect would be subtle, but measurable by instruments like JWST, ALMA, or the upcoming ELT arrays. And there's the most ambitious test of all, time correlation. If 3i Atlas's light output is modulated by structured processes, either natural lattices or plasma oscillations, Then its brightness should contain harmonics, faint periodicities embedded in the noise. Detecting such structure would require long, uninterrupted observations, days of continuous monitoring to catch the pulse of the system. If we find those signatures, flickers, jumps, harmonics, synchronized multi-wavelength shifts, the implications will be enormous. It would confirm that we're witnessing not simple sublimation, but an active, dynamic process of energy transfer, a system alive with internal feedback. But if we see none of them, if the glow remains perfectly smooth, perfectly static, that too would be an answer. It would tell us that 3i Atlas is governed by physics so steady, so balanced, that even our most sensitive instruments can't see it waver. And that, in its own way, would be even stranger. Because every living system flickers, even stars. To remain motionless in light would mean something else entirely. A stability beyond equilibrium, a phenomenon so self-contained that it refuses to reveal its pulse. Either way, 3i Atlas will teach us something fundamental. Whether light itself can remember, whether chemistry can mimic intention, and whether the universe, in its quietest corners, still keeps a few secrets just beyond the reach of our instruments, waiting for us to look again. Has NASA or other agencies deliberately downplayed these anomalies? Probably not. Real science is messy, and rival teams want announcements. But in institutional narratives, anomalies are often smoothed out. The deeper question, how many observations are quietly filed away because they don't fit? Every great mystery eventually meets the same fate: bureaucracy. Discovery begins in wonder, a strange signal, an unexpected glow, a number that refuses to behave. But before it reaches the public, it must pass through the filters of caution, confirmation, and consensus. That's not conspiracy. That's procedure. Yet somewhere in that process, something vital can be lost. The awe of not knowing. In the case of 3i Atlas, no agency has issued a cover-up, no coded silence. Data flows in from observatories across continents and from orbit, published in open repositories. The science is there for anyone with the patience to dig. But what is true is subtler, and perhaps more interesting. Within institutions, anomalies rarely make headlines. They are uncomfortable. They complicate narratives, dilute certainty, and challenge models that have funding attached to them. It's easier, safer, to classify them as noise, to move on to the next dataset that behaves. When 3i Atlas first began showing its strange green emission, the discussion threads on internal channels lit up. Some proposed data reduction errors. Others blamed calibration drift. A few raised the possibility of unknown emission species. Within days, the language softened. Outlying values, unverified signals, likely instrumental. What starts as a revelation quickly becomes a footnote, not because of malice, but because the machinery of consensus cannot move at the speed of discovery. NASA, ESA, the NSF, these are not monoliths, but constellations of competing minds. Within them, there's no single hand guiding the story, only inertia, the slow pressure toward coherence. Every scientist knows this tension, between the thrill of the anomaly and the obligation to make it behave. The truth is that science is built on editing. Every paper trims away uncertainty. Every press release highlights what fits. The result is a public version of discovery that feels linear and clean, when the real process is anything but. So no, there is no grand conspiracy. There is only the quiet gravity of the familiar. Anomalies like 3i Atlas don't vanish because someone hides them. They vanish because our language for them hasn't caught up yet. Our instruments see things our theories can't describe, and until the two align, those things live in limbo, archived, unexplained, and quietly extraordinary. It's happened before. The first pulsars were dismissed as scruff on a radio readout. Quasars were called quasi-stellar nonsense. The cosmic microwave background sat unnoticed in data for years. Every epoch of astronomy begins with ignored signals. The difference between a mystery and a discovery is simply how long someone is willing to keep looking. In this light, 3i Atlas becomes less a case of suppression and more a test of patience. How long will we let the data breathe before we decide what it means? How much silence will we mistake for certainty? Perhaps the true conspiracy isn't institutional, it's psychological. The human brain loves closure. We crave neat categories: comet, asteroid, rock, ice, artifact. But the cosmos doesn't share that need. It prefers ambiguity. It thrives in the spaces between definitions. And maybe that's the deeper lesson of 3i Atlas. It doesn't need to be hidden. It only needs to be complicated to be forgotten. The signal that doesn't fit is the easiest one to overlook, not because someone told us not to see it, but because we stopped expecting to. So the next time an agency report glosses over an anomaly or a press release rounds an irregular number, it isn't evidence of deception. It's evidence of discomfort, a system built to explain the universe struggling against the parts of it that refuse to be explained. The conspiracy, if there is one, is not of silence, but of simplification. The need to make the cosmos tidy when it never was. 3i Atlas is untidy. It glows when it shouldn't, darkens when it should shine, resists every model we build for it. And that's not a scandal. That's science doing what it was meant to do. Standing at the edge of understanding, staring into the green, and not yet having the words. Throughout this investigation, we must remember, we are interpreting with human categories. When we say unexplained, it doesn't mean supernatural. It means unknown. The mystery teaches humility about chemistry, cosmic scale, and our limited vantage point. We keep forgetting that every telescope is, in the end, a mirror. It reflects not just the cosmos, but us, our expectations, our fears, our habits of seeing. When we look at 3i Atlas, we are not simply observing a body of ice and rock from another star. We are watching the limits of our own comprehension light up in green. The data tells us what is there, but the interpretation reveals who we are. Science has always lived in this tension, between precision and projection. We measure the spectra, the polarization, the velocity, but beneath it all is interpretation. The story we tell ourselves to make the numbers coherent. Comet, visitor, anomaly. These are human words. Nature doesn't use them. It only moves, reacts, shines. And so when 3i Atlas behaves in ways our models can't predict, we reach for new language because silence is unbearable. That's what makes this investigation as much philosophical as physical. The green light, the missing lines, the impossible stability, all of it becomes a mirror to our need for order. We see a pattern and call it meaning. We see noise and call it mystery. But the universe doesn't care what we call it. The glow is not trying to communicate. It's not hiding secrets. It simply is, and we are the ones who turn that being into narrative. There's an irony here. Every time humanity encounters something that doesn't fit, our first instinct is to imagine intelligence behind it. An architect, a signal, a plan. It's the oldest reflex of consciousness, to find ourselves in the unrecognizable. We did it with comets once, calling them omens. We did it with lightning, with magnetism, with radio signals. And now we do it again, with an object from another star. Perhaps that's inevitable. After all, meaning is the one element we always bring with us. But the real humility begins when we stop insisting the cosmos speak our language. Unexplained doesn't mean impossible. Strange doesn't mean intentional. Sometimes the most alien things are simply natural processes wearing forms we haven't yet seen. If 3i Atlas teaches us anything, it's that our categories, comet, star, artifact, random, are scaffolding, not truth. The universe moves freely between them, unbothered by our boundaries. Maybe that's why its beauty hits us so deeply. Because in it, we glimpse something beyond analogy. A reminder that our minds are still small, still provincial, still learning to read the larger patterns of existence. The green light is not a code to crack. It's a mirror to our curiosity. It asks not, "What is this?" but "Why do you need to know?" And yet, that hunger to know is sacred. It's what built the telescopes, launched the probes, and led a species bound to one world to reach into interstellar darkness for meaning. To investigate something like 3I Atlas is to confess wonder, to admit that, despite centuries of data, we still stand at the edge of the unknown, humbled and enthralled. The most dangerous illusion isn't that 3I Atlas might be alive or engineered, it's that we have nothing left to learn. That arrogance is what turns science into dogma, curiosity into comfort. But the universe resists comfort. It keeps offering us questions that unmake our certainty. The moment we think we've mapped the rules, something like this drifts by, silent, luminous, patient, to remind us that reality is wider than theory. So perhaps the real discovery here isn't out there at all. It's internal. Every unexplained spectrum, every impossible ratio, every missing line is a reflection of the space still unexplored inside us, the parts of our perception not yet trained to see. 3I Atlas, for all its chemical puzzles, might simply be showing us what humility looks like in motion, a traveler indifferent to our questions, reminding us that awe is not ignorance, but participation. When we say we don't know, we're not confessing failure. We're performing the oldest act of science, the admission that knowing begins with wonder. The green light isn't a revelation, it's an invitation. To look again, to ask better, to accept that our models are only ever temporary lanterns in a cosmos too vast for any final understanding. Maybe that's the quiet message encoded in 3I Atlas's passing, that in studying it, we're really studying ourselves, the way we reach, the way we interpret, the way we stand before the unknown and insist on giving it a name. In the end, perhaps the glow we see isn't just a chemical anomaly, but a mirror held up to humanity's most beautiful flaw, the refusal to stop asking. At dawn, the night recedes. The green glow fades, but its presence lingers in our instruments, in the questions we can't yet answer. We exit into silence, but not emptiness.